So the next topic after gas turbines for propulsion is compressible flow. And compressible flow, there's two big things we want to cover. Speed of sound, especially in air or gases, and then also converging, diverging nozzles. I wish we had more time. We don't have a lot of time for these topics, so it's a good introduction to them. This is an image of a military aircraft approaching the sound barrier. And when you approach the sound barrier, when you get close to Mach 1, and then you go over the sound barrier, you're going faster. Some very interesting things happen, like here they're just showing a condensate white halo in this vicinity and that vicinity, where there's a shock wave. I'm not an expert in shocks. I took a whole class in compressible flow. That did not make me an expert in compressible flow, believe me. But you just have to really work with it. But they are very practical, and there's compressible flow effects, especially shocks, in real applications out there. So wish we had more time to spend more time on it, but we don't. I like to introduce students to people who were some of the pioneers in the area. This is Robert Goddard, who died in '45. He is basically known as a modern rocket. For developing modern rockets and propulsion that actually went into space. He was a professor in Worcester, Mass. This is an image of him with one of the early rockets. You know you make it when NASA names one of their space flight centers after you. The NASA Goddard Space Flight Center. That's a pretty big deal. Where is that one at? Maryland. So also, you know you really made it, although he's deceased by this time, sorry. You're on the postage stamp. And this is a fairly recent book, 2004, The Rocket Man. So it's a very good read. Can a rocket produce thrust in a vacuum, especially in outer space? Well, in the 1920s, they ran an article in the New York Times about a professor who believes that a rocket can reach the moon. And the next day, January 13th, front page story after the story about Goddard's rockets, a New York Times editor wrote an editorial entitled "A Severe Strain on Credulity." Basically, it's unbelievable. And in it, it's quoted that Professor Goddard does not know the relation of action and reaction. Doesn't that sound like, isn't that true? Action, reaction, I push on you, you push back on me. If I push on that wall is pushing back on my hand. That all makes sense. And of the need to have something better than a vacuum against which to react. That seems appealing. It's like, hold it, a vacuum can't push back on the rocket. Of course, that's Professor Goddard, only seems to lack the knowledge ladled out daily in our high schools. Oh my. They really cut him down, didn't they? Anyway, he went on and yes, we can have rockets in space. Because what really makes a rocket work? It's the M dot coming out the exit. And if you have on board the fuel and the oxygen, and it combusts that way, the forward thrust is, like a lot of people gave it to me, is just the mass flow rate times the exit on the velocity, exiting. Because there's no inlet. Fuel and inlet, it's on board the rocket. So there it is. Does it need to push against something? Not really. No, it doesn't. You just need to spew it out in the back. And you need to spew it out fast. So we want to talk about the speed of sound before we talk more about nozzles, especially converging, diverging nozzles. Well, what is the speed of sound? Well, we can develop it, and will very shortly, but I'm going to do it very quickly, as a property where it's defined as the square root of the change in pressure with respect to density holding entropy constant. That looks pretty mathematical and abstract, doesn't it? It sure does. But using that definition, we can get to a relationship that some of you may have already been exposed to and already remember, and hopefully after this class you will remember. that the speed of sound in air is given by this very simple equation, the square root of kRt. We like things that give us simple equations, don't we? So what are all the parameters in this equation? Again, the symbol C is for the speed of sound. It's in an ideal gas. I should even change that to be just an ideal gas. And what is K? Specific heat ratio. If it's air, it's 1.4. If it's something like helium, you know, it's like 1.67 or something. It's monoatomic. But a lot of gases, they're diatomic, and it's about 1.4 for room temperature. It's slightly a function of temperature, but it's primarily a constant. What is R? Gas constant, so it would be R bar, the universal gas constant, divided by the molar mass. And what is T? Temperature, absolute scale. Now this is why some kids, I've never done it, I've never been to a little birthday party where somebody has a helium balloon and they open it up and they draw into the helium into their lungs. I've heard it's been done, and then they speak. And they sound a lot different, don't they? And that's because of the difference in the molar mass of the helium and the sound wave coming out through the helium. So I don't know, does it make them sound like they're chirpy, or does it make them sound like a deep voice? Like a chirpy? There you go. All right. So please don't say you were practicing and Manteuffel said do an experiment, so you're boiling helium and sucking into your lungs. Don't do that. I don't know how safe it is. I'm pretty sure it's safe, but a lot of people seem to have done it at parties. How many people have seen somebody do it? Wow. Wow. All right, so this is a very simple equation. Let me ask you this. Does the speed of sound in air depend on the pressure of the air? Well, you just break it down. Does K depend on pressure? Does R depend on pressure? The molar mass depend on pressure? The temperature depend on? No, which is very interesting. As long as it's an ideal gas. Now you can take air and put it up to such high pressure that it doesn't behave as an ideal gas anymore, but then this equation doesn't work. You've got to go back to this equation to calculate from first principles the speed of sound in that material that's no longer an ideal gas. The next thing, once we have the idea of the speed of sound, we have the Mach number. Mach number is simply the ratio of the actual speed to the speed of sound in air. I'm going to cover a derivation that's been covered before and published out there, but let me go through this. One is, I'm going to say your physics textbook has probably a great description of this and a great derivation of this. Remember that 3-inch physics textbook you got tired of carrying around? Yep. It's really well written, and I encourage you to go back and look at it, as well as this derivations in our thermodynamics text, as well as probably just out on the internet, do a Wikipedia search or something. But this is the basic way they develop it. They have a little piston, and the piston sort of moves and it produces a little pressure bump so that the pressure in the stationary fluid before it, and it's easier to think about one dimensions, forget about multiple dimensions, let's do 1D, little pressure bump going down. And so the pressure gets, before is all constant, and now we have this bump coming down because of the impulse of the piston. So behind it, there's a pressure plus delta P. There's been a bump in pressure. And in front of something, this is a moving wavefront, the velocity is stationary, but behind it, it's moving at dV. So we have this moving wavefront caused by this disturbance of a piston. So the stationary fluid behind it, then we have moving fluid behind it at higher pressure. It has a higher enthalpy, higher density, etc. Well, we want to analyze it. We do a little control volume around the moving front. We have that moving front not accelerating, it's moving at a constant speed, so we can take a look at what comes in on the right side, what goes out on the left side. We do a mass balance. This looks really easy, just a mass balance. Rho V, which is the speed of sound, and then A. So rho VA. But what do we have on the left side? We have, it's really a different speed, the same area and a different density. So, but when we multiply, we're thinking, oh, this is a small density change and a small velocity change. So you cancel the smalls times the small, you neglect the higher order terms, the two small terms, and you just get this equation. It looks pretty abstract, don't you? But it's a mass balance. It's coming from a mass balance. Then you do an energy balance. Does enthalpy plus the kinetic energy look reasonable? Sure. And on the left side, you have just a different speed for the kinetic energy going out and slightly different enthalpy. We combine it to give you this simple equation. So if the enthalpy changes, the speed changes. And there's a constant C. We also have entropy balance. Easiest way to do the entropy balance, we're going to have isentropic change in that control volume. So we have a TDS relation. We say the change in entropy is 0. And now we have a relationship between enthalpy change, specific volume, and pressure. So we used mass, we used energy, we used entropy. I need to go to the next slide. There's the finishing off of the entropy. So these are the three equations, mass, energy, and entropy. And we need to combine them. It's algebra at this point. Get rid of the delta H. And then substitute in, and you get ... C squared is equal to the change in pressure with respect to density. That was all based on constant entropy. And so you take the square root. If you want to get back to the equation we just talked about, C is equal to square root. I know there's a lot to swallow. There are better derivations out there, but let's press forward. If you now work with an ideal gas, in an ideal gas undergoing isentropic process, is PV to the K a constant? Yes. So we can say P is equal to a constant times rho, which is inverse of V to the K. Then we take calculus, differentiate that with respect to rho, holding entropy constant. You get this, boom. You just do the math, the substitution. You plug it into the equation, and you get that C is square root of KRT. It's kind of like, I know how to differentiate and then do a little algebra. So there's the derivation of a very fundamental equation in compressible flow. Mach. So we take that speed of the substance in the fluid, we divide by the speed of sound in the fluid, and that gives us the Mach number. If the Mach number is less than 1, we say it's subsonic flow. If I pick up a piece of paper or something and I throw it in this room, that's an object in the speed of, it's Mach. It's not going even close to speed of sound. But then you can get things going right at the speed of sound. You would be Mach 1, sonic. Then you could have transonic. It's around Mach 1. A little low, a little above, but it's around Mach 1, transonic. Supersonic, hey, that object's going faster than the speed of sound in the substance that it's flowing through. Can you get an object flowing faster than the speed of sound in air? You sure can. And hypersonic, so the Mach number is much, much greater than 1, probably greater than about 4, 3 would be hypersonic. I don't know the cutoff, the demarcation between hypersonic, but those are the terms. Now let's talk about a nozzle. What is the purpose of the nozzle? Let's just review our basic subsonic nozzle. What do we want that nozzle to do? Get it out with high speed. And so you're going to make a device like a jet engine, and back of it you're going to put a nozzle. So we now need to understand nozzles. And guess what? We want some of our jet engines to help us go over Mach 1. It's going to take a very specific type of nozzle. It's going to take a converging, diverging nozzle, and this always blows my mind to think about it. But before we go into converging, diverging, let's talk about just a simple subsonic nozzle, and sometimes it's tricky. All right, so we're going to compare the area exit compared to the area inlet. Which one is bigger? For a simple converging, it's a converging nozzle. It's a subsonic nozzle. We're going to talk later about it converging, diverging. First it converges, then it diverges. That's the area change. So a subsonic nozzle converges. As it converges, what does the velocity do? That's right. Exit bleed speed is going up. What about the pressure? What happens to the pressure as you're going through? It's going down, isn't it? Okay. What about the entropy? Up, down? Same? It's a very good nozzle. It's one of these things that stays the same. In a simple analysis of a nozzle, we're not going to try and model friction, which would mean that the entropy is going down. Right? Second law analysis, the best is this entropy is not generated. Boom. It's isentropic flow. How about the kinetic energy? Kinetic energy of the outlet. What do you think? It's higher. How about the enthalpy? Lower. And what we're doing in our mind, we're doing energy balances, we're thinking about the second law, we're thinking about mass balance. And so it goes like that, isn't it? Because an energy balance is enthalpy 1 plus the kinetic energy 1 is equal to the enthalpy 2 plus kinetic energy 2, right? And so the change in the kinetic energy, which is KE2 minus KE1, plus the change in the enthalpy is equal to 0, H2 minus H1 is equal to 0. So if the kinetic energy goes up, the enthalpy has to go down. What about the temperature? And what you're doing is you're saying that basically the temperature times the specific heat minus a reference temperature is the enthalpy. So enthalpy is only a function of temperature. So if the enthalpy goes down, guess what the temperature does? Goes down. How about the specific volume? This one's tricky. Same? That's a good guess. Well, how about this? Do you remember a relationship where let's do this one. P2 over P1 is V1 over V2 to the K. What does that apply for? Ideal gas, isentropic process, constant specific heats. We're applying constant specific heats. And so you can get that. How do I unravel this one? Or another way to look at it is put it on a PV diagram, and I have two lines. I have a line of higher temperature and a line of lower temperature. And I started at high pressure, high temperature. That's inlet state 1. I'm going to go to a lower pressure and a lower temperature. That's state 2. That is my isentropic expansion. What happened to V? V2 is greater than V1. And the last, because a lot of times in the compressible flow literature, they talk not about only specific volume, they talk about density. What about the density? The reciprocal of the specific volume, so it's just the opposite. True? Density went down as it went through. All right, that's a good warm-up. Let's solve a problem. So we have a converging nozzle, and it has an inlet temperature of 300 K. Again, this is converging nozzle. Let's go ahead and draw it like that. And we're going to give the temperature inlet is 300 Kelvin, and the pressure inlet 120 kilopascal, and the exit pressure P2 is 100 kilopascal, and the exit area A2 is 10% of the inlet area, so it's 0.10 times A1. So I don't know what A1 is. They didn't give it to me, but I know A2 is only 10% of it. So if I wanted to try and draw it accurately, there's a big area, and it's only 10%. Really small area, right? Okay. Assume the flow is isentropic. Using constant specific heats with C sub P and K given, determine the exit temperature. can you find T2? Well, this one, how would I find T2? Well, I would assume that it's an ideal gas, right? And I have relations for isentropic flow, ideal gases undergoing isentropic expansion or compression. And one of the relations would be that the exit temperature T2 divided by the inlet temperature T1 is related to the exit pressure divided by the inlet pressure raised to the K minus 1 over K. Did they give me the inlet and outlet pressure?
Yes.
And they gave me K. So I just use that equation and I calculate exit temperature, 284.8 Kelvin. Exit speed. What is my exit speed? Well, let's try an energy balance, right? Yeah, so if we try the energy balance, we have energy balance. We have H1 plus the kinetic energy 1 is equal to H2 plus the kinetic energy 2. All right, we can rewrite that as C sub P T1 minus T2 is equal to 1/2 V1 squared minus V2 squared. I have one equation. I'm looking to calculate V2. I know everything but V2 and V1. But you don't really have to pick V1. What you can do is you can come and do a mass balance. You had an energy balance. You can do a mass balance and actually get a relationship between V1 and V2 and then have two equations, two unknowns, and then solve for the one unknown of interest. So what is our mass balance? Well, we have the mass flow rate in is equal to the mass flow rate out. That's not too bad. We have the density in plus the area in plus the velocity in is equal to the density out times the area out times the velocity out. If the densities didn't change, it would be a lot easier. But unfortunately, the densities aren't the same. So we have to substitute what is rho 1, that's P1 divided by RT1. And we have the A1, V1. And then for rho 2, is it at P2 divided by RT2? A2, V2. We use the ideal gas equation, cancel the R's. And then we can rearrange and solve for V1 is equal to V2 times P2 over P1 times A2 over A1 times T1 over T2. Now we'll take and substitute in. Aren't you glad you took a college algebra class? Substitute in and do a little algebra, and we solve for V2 is equal to the square root. I'm just going to give you the answer. 2 specific heat constant pressure T1 minus T2 divided by 1 minus P2 over P1, A2 over A1, T1 over T2. It's not trivial, but there it is. It's almost a miracle that it works this way, because I really don't need to know the inlet speed. I can actually, at the exit speed I'm able to calculate. I can go back and calculate the inlet speed because I had two equations, two unknowns. I can go back and calculate both unknowns. But we're able to calculate for this problem that V2 comes in at 183.2 meters per second. Hey, we already know the temperature, so we can calculate the speed of sound, the square root of kRt at the exit. And so the speed of sound at the exit, C2, comes in at 338.3 meters per second, and the Mach number exit is 0.5416. Yes, sir. I'm sorry?
The red arrow pointing up to the velocities.
Yeah. So I take and get rid of this V1 by substituting in for V1, and I have to square it and then proceed on.
Yeah, but I think those V squares are switched around. I think it's supposed to be V2 squared minus V1. No?
Is it?
If you start from the equation above it, yeah.
Yeah, you may be right. Yeah, I think you're right. It's yeah, I think it's 2 minus 1, right? And then yeah. Okay, let's do this. Let's vote. Does this equation look good? Yeah. And then all we have to do is we'll have H1 minus H2, and then we'll have kinetic energy 2 minus kinetic energy 1. That look good? And then C sub P times T1 minus T2, and then this is 1/2 V2 squared minus V1 squared. And now we're right where I left. Thank you for correcting me. Do we agree? Thank you very much. How many other people were stumbling on that? Sorry. Yeah. All right. So we calculate the Mach number. Now the other thing is, how could I get it to go out faster?
Decrease the area.
That's one idea. Decrease the exit area. Instead of 10%, 2%. How else? What else other than just changing the area? Use your intuition. I want it to go out fast. How about this? Make it hotter coming in? Or making higher pressure coming in? Let's say I had 3 things to pick from. I have choice A. I'll make A2 smaller. Choice B, I'll make T1 greater. Choice C, I'll make P1 greater. Which one would you pick? You only have one thing to do. You can only tweak one of these. How many people would say, give me the higher pressure on the inlet? A little intuition, but yeah, that'll work. So the next page is a little hard to understand. Let me break it down for you. We just replay this problem over and over again. The equations work. So here is the area ratio. What did we just have for our area ratio? Was it 20%, 10%, 5%, 1%, 0.5%? What was our area ratio for the problem we just solved? It was 10%. So we're somewhere in this column. Now on the other axis, you have the inlet pressure. Now, what was the inlet pressure? 110, 120, 100, it's going up. The inlet pressure is going up. I could have done it as ratio pressures, but I put it. What was the inlet pressure for this problem? 120. What did we calculate for our exit Mach number? 0.54. So that's all the numbers. So everything in green, all is the Mach number. This is the Mach number. How did we calculate it? Give me the inlet pressure and give me the area. So let's say I'm at 0.54 and I want to maximize it. If I make a smaller area, smaller area, smaller area without changing the pressure, the Mach goes to 0.53, 0.52, 0.52. It didn't increase the Mach, did it? Yeah. Let's go down here. It's not the right term, but you got the idea. Let's increase the pressure. Oh, look at it. It's 0.65. It's 0.74. You just take the same equations. Just change the pressure inlet. Until you get right here, 0.9, 0.99. What's this? 1.04. Mach over 1. 1.08. 1.12, etc. Guess what? These are dreamland. If you try and build one and tried to make it work, it wouldn't stay. It wouldn't come out supersonic. Every place in here, it's supersonic. Can you see that? Right like that? I guess that's supersonic. Everything in here, everything in there is supersonic coming out. Guess what? That nozzle will not work. It will not produce supersonic exiting gases. And that always trips. It's like, this is incredible. Why? Well, you two things. One is you need a supersonic, you need to get it to be choked flow in a traditional nozzle like this. But then you need to do this, and you need to expand the area. And if you have a nozzle like this, which is both converging in one section to a throat, and then diverging, making the area getting larger, you can get the gases to come out supersonic. Guess what? Why is that true? Well, it has something to do with the entropy and shocks. And we'll pick up there next time, but that's a good lead-in for converging, diverging nozzles.